doesn't really matter. I have some organizational topics first before we continue with our class. First of all, last Monday, I told you that we have to repeat the Friday class that didn't take place last week, and that we will do that by simply extending our Friday classes by 30 to 45 minutes in the next week and in 2 weeks to come. So this week is a regular class, 90-minute class, and next week we will simply use some time of lunch break to extend our class. We will do the same in 2 weeks. So for the students who have another class at 2:15, it shouldn't be any problem. Okay, that's the first thing. The second, there will be a tutorial starting next week. I will just write it here. It starts it will be on Tuesdays. Tuesdays at 2:15 in which room? 5104. 5104. Number of participants is 40. So max participants is 40 students, and Mr. Akash Ralhan will give the tutorial. So starting next week for 90 minutes, every Tuesday starting at 2:15. And there are, well, it will be in present. Will the class extend in the lunch break only on Fridays? No, the class, we have to repeat one 90-minute class that did not take place last week. So Friday next week and Friday in 2 weeks, we will extend the class by 30 to 45 minutes, not on Mondays. Okay, so only on 2 Fridays, the next 2 Fridays, our class. The tutorial is in presence in 5104. I don't know, actually. I guess in the can register in the e-learning course. There's always an e-learning course for the tutorials where all the tutorials are stated, German and English. And there you can, well, at least last semester, you could register in the course. Monday next week is no class. Monday is a holiday in Germany, well, in Bavaria. So there's no class on Monday. Okay. All right. Do you have anything else? No, that's it. Okay. So let's have a look at our script. So we did some exercises in the last 2 weeks regarding chapter 2. And of course, it's a big chapter, and there will be more exercises to come before we continue with the third chapter. But there's one theory part that I would like to discuss first. It's like the last part here on page 9, the kinematic conditions. Because kinematic conditions is important for most systems when we have wheels or connected by ropes and additional masses and things like that. We need to find relations between the motion of these subsystems, between these masses. And I will give an example for this very simple case, pure rolling of a cylinder, and how the kinematic conditions are derived. And then we will do some exercises deriving kinematic conditions for different type of problems. So we have the cylinder right here standing. Oh, wait, I have to remove this thing. Okay. We have the cylinder right here. And if it's stated that a cylinder is performing pure rolling, it means that there's no sliding between cylinder and surface. Okay, and this in this case, we have a velocity of the center of the cylinder, similar to the wheel that we discussed 2 weeks ago, last week, Monday last week. So this would be the velocity of the center. Let's assume that the cylinder has a certain radius, r, and now the cylinder rolls along this surface with an angular velocity. And now for any other point on the cylinder, we can apply our standard approach, saying, okay, in case of rigid bodies, one point moves as the other, translational part, and at the same time, this point rotates about the other point. So for example, for this point A right here, we could say that the absolute motion consists of translation as our center point, because we know the velocity there, and rotation of A about C. And rotation of A about C, velocity in case of a circular motion, as radius times angular velocity. So in this case, radius distance between A and C is the radius r times omega. And according to the definition of the velocity pole, these velocities have to be of same size. The absolute velocity in point A, in case of pure rolling, is equal to 0. I'll just state it here as well. So if we simply sum the velocities in point A, then this results in the absolute velocity of A. Since the vectors are parallel, we do not have to state them as vectors. We can use the values. And that has to be 0 in case of pure rolling. And from this equation follows that the velocity of the center of gravity is equal to r times omega. And this relation is our kinematic condition. So that means a kinematic condition, as stated in the text above, is a relation between the two types of motion. In this case, translational and rotational motion. Translation and rotation. And once we derived the kinematic condition for one of the variables, distance, velocity, or acceleration, this kinematic condition is also true for its time derivatives and time integrals. So in case of our kinematic condition, which is Vc is equal to R times omega, we could integrate over time, which leads to x is equal to R times phi. Distance traveled is equal to the arc length covered. Or we could build the time derivative. The acceleration of the center of gravity is equal to radius times angular acceleration. Okay, so that's important to keep in mind, because some might prefer building the kinematic conditions in terms of velocities, others in terms of distances traveled, but that really doesn't matter, because you can simply build time derivatives or integrate the kinematic condition to find the condition needed for your equations. Okay. Now, of course, this is a simple example, and we can memorize that. We do not have to derive this every time in case of a cylinder. We simply memorize that the velocity of the center of gravity is equal to R times omega. But of course, there might be other problems. And usually in the exam, there is one problem where you're asked to, or maybe even two problems where you're asked to derive the kinematic conditions and where the kinematic conditions are needed to solve the problem. Because the kinematic condition gives an additional equation that helps you solve the problem. Okay. So I would like to discuss some more complex examples from the exercise book. We'll start with exercise 211. Here. Okay, what do we have? We have a cylinder with an offset, a small radius is given, and the big outer radius is equal to 3 times small radius. The small radius is the given value. And the cylinder rolls to the left with a velocity v1 in the center of the cylinder. And then there's a block connected to the cylinder by a rope, and this block slides on an incline. The angle of inclination is given by beta. And we have to find the kinematic conditions and express the angular acceleration and the acceleration a2 dependent on the acceleration a1. Okay, so we have to find the kinematic condition, the relation between our angular acceleration and our acceleration of the cylinder and the acceleration of the block. So what do we have to do? First of all, we will start with a diagram, a simple figure that helps us solve and derive the kinematic conditions. You see that there are no directions given for omega and v2, so we do not know them right now. We have to find them as well. But of course, omega can be seen from the figure. Okay, let's start with, no, wait, I'll make this a little bit bigger. With the cylinder. Okay, what we know is the velocity and the acceleration, the center of gravity of the cylinder. So I will derive the kinematic condition in terms of velocities. Then we have v1 here. Then this is the contact point between cylinder and surface. And this point right here is where the rope is connected. So we have to find relations for both of these positions. I will start with the bottom, the contact point to the surface. And we do exactly the same as in the previous example. So we can state that the cylinder at this point down here moves translational as the center of gravity. And at the same time, this point rotates about the center of gravity. Now we have pure rolling as stated in the problem description, which means that our pure rolling condition that we memorize has to be applied here as well. Now we have to be careful. The radius is capital R times omega. In consequence, omega has to point this way. Then from this relation, we know that the velocity is 0. That's the velocity pole with minus V1 plus R omega. V1 is equal to R omega, or using the relation above, 3 small r times omega. Okay, that's our first relation. We can build the time derivative of this relation, stating that A1 is equal to 3R alpha. And we have to express alpha independence of A1, and we have to rearrange. Alpha is 1 over 3R times A1. So that's our first kinematic condition. Okay, then for the second point, the point where the rope is connected. Again, this point moves translational as the center of gravity. And this point rotates about the center of gravity. Now in this case, with small r times omega. But at this point, the absolute velocity is not 0. That's not the velocity pole of the system, meaning that the velocity here is not 0. But we know due to the connection of the rope with the second block, the absolute velocity has to correspond to the velocity of the block itself, V2. Then we can state the equation for this point. For example, summing in this direction, absolute velocity V2 is equal to V1 minus R omega. Okay, that's our second relation. Now we simply have to rearrange to state this equation in dependence of A1. First of all, we build the time derivative. A2 is equal to A1 minus R alpha. And then we have to substitute alpha, A1 minus 1/3 A1, which is 2/3 A1. So this is our second kinematic condition.
Professor,
yes.
V2 is the speed of the block?
Yes, velocity of the block. Okay, we have 3 different variables, kinematic variables, okay? So if you're not sure how many kinematic conditions you have to derive, and it's quite clearly stated in the problem description, but if there's a situation when you're not sure about the number of kinematic conditions, it's quite simple to find, because here our kinematic, about not maybe given is the wrong word here, but the number of our kinematic variables, A1, alpha, and A2. We have 3 kinematic variables. That means we need 2 kinematic conditions, always one less than the number of kinematic variables given. Okay, so that's how you find the number of kinematic conditions if you're not sure in the system that is given. Okay. This only works when our subsystems, our individual masses, are connected by ropes or rods, for example. If there's a string connection, it does not work like that. Okay.
Sorry, Professor, why did we make 3 minus 1 again?
Excuse me?
Why did we make the 3 minus 1 for the kinematic conditions again?
Find the number of kinematic conditions. It's always one less than kinematic variables in our problem, just to know how many kinematic conditions we have to derive.
Okay, thank you, Professor.
Okay, let's have a look at the second example. How do we know which ones? Well, the kinematic variables are all the only variables we know in kinematics, which are A, 1, 2, 3, 4, 5, and alpha. Of course, you can either choose accelerations or velocities or distances. Don't mix them. So A and alpha, or V and omega, or X and phi. So either you count the number of accelerations or the number of velocities or the number of distances. Okay.
Sorry.
Yes.
Excuse me.
Yep.
I wanted to ask concerning the A2. Why was there no angular velocity included in the equation, where A2 is equals to A1 minus R alpha?
It's accelerations, it's not velocities. And alpha is the angular acceleration. And then I substituted alpha from here to here, because the task was to express A1 independence of A2 independence of A1, not independence of alpha.
Oh, okay.
Okay, so here it says A1 as function, A2 as function of A1 and alpha as function of A1.
Okay, I'm sorry for dragging you back, Prof.
No, that's okay.
Okay, I noticed that you work in scalar quantities, and I do mine with in vector quantities. And I noticed that for you to get, for example, now, V1 against V2 is more like relative velocity of both sides together. Once you have V1, you can use the relative velocity of V1 to get V2. So there is always a formula which it flows, which it goes with together, whereby, for example, between A2 and A1, it should I have it as A2 equals to A1 minus A1 plus R alpha, then minus omega R. So I wanted to ask, is there any form of rotation between A2 and A1? Though once I apply my signs, my directions together, I end up having this equation. But that's why I was confused why there was no angular velocity conveyed in it.
I'm not sure if I understood your question correctly, but so the second object, the block, is only moving rectilinearly. So there's only a translational motion, so a V2 and an A2. And the cylinder is translating and rotating at the same time. So we have to consider both. And it's for the color coding is always that red is the absolute velocity, purple is the translational component, and green is the rotational component. So in this case here, for this equation here, I said, okay, the absolute velocity in this point where the rope is connected has to be identical to the velocity of my block. Of course, there's a rope in between. And from the cylinder's point of view, this velocity consists of two components, translation and rotation, because the cylinder moves forward and it rotates. So I have to add them. It's a vector addition, of course. That's why, but the vectors are parallel. So, but then I have V1 minus R omega because the vector of the rotational component points in opposite direction. And then once I build the time derivative, there is still the angular component in the equation. But then I use the relation I already found for alpha and substitute it in the equation. And then as a result, I can express A1 independence of A2 independence of A1.
Okay, thank you very much.
Yeah, okay. Okay, second example. Problem 212. So we have a cable drum. The running radius is given. The outer radius is given again with 3r. And it also rolls. Rolls always means without sliding on a conveyor belt. The velocity is given as well. And we have to find the kinematic conditions and express the angular acceleration and the acceleration of the center of gravity independence of A1. So the kinematic relations of the cable drum independence of the acceleration of the belt. Again, don't worry too much, because I think often it happens that you see a system and you think, oh, I don't know, there are too many parts in it and it's a confusing motion. And just don't worry too much about it. Just free your masses and just use the standard approach, absolute velocity, translational component, and rotational component. And we do the same here. Okay, so again, I will draw the cable drum. And I will draw the belt below. Okay. Now the belt moves with given velocity and acceleration. Again, I derive the condition for the velocity because I know that in case of pure rolling, I have a velocity pole. The absolute velocity is 0 in this point. That helps me deriving the kinematic conditions. Now, the center of gravity moves with velocity v2, and the belt rotates. There are no directions given for the cable drum, for velocity and angular velocity. But of course, if I think about it, the cable drum is sitting on the belt and the belt moves to the right. Then in consequence, our cable drum has to rotate in this direction with omega and alpha. Okay, that's the only option there is in case of pure rolling. It has to move in this direction. Then I know that in this point down here, the translational component is equal to capital R times omega. Then I know that it rolls and does not slide, then this has to be my velocity pole. I can also include this here first. Draw it here. R times omega for the small radius. There's a belt the rope connected, and here it rolls along or from this rope without sliding. Should be a horizontal vector, of course. Sorry, it's horizontal. Okay. So this is the small r times omega, small radius times omega. Then the velocity due to translation has to point in opposite direction. V2 and V2. Now, I'll just draw on the big figure. Here's the connection with the rope. The rope can be considered as a surface, a non-moving surface. And our cylinder simply rolls along this surface. There's always tension in the rope, okay? So this point here is our velocity pole. Then we can state that 0 is equal to V2 minus R omega. In consequence, we can rearrange V2 is equal to R omega, and we can build the time derivative saying that A2 is equal to R times alpha. We do not know alpha yet, so we have to leave it like this and move on to the second position, the contact point between cable drum and belt. And here we consider this situation. We know the absolute velocity has to coincide to the velocity of the belt. So the absolute velocity here is V1. And this absolute velocity consists of our translational and our rotational component. Capital R times omega minus V2. Capital R is equal to 3 small r times omega, and V2, know from the first condition, is equal to R times omega. So this is 2R omega. V1 is equal to 2R omega. We build the time derivative. A1 is equal to 2R alpha. And we want to express alpha independence of A1. Then we have to rearrange the equation. Alpha is equal to 1 over 2R times A1. So this, oops, sorry. This is our first kinematic condition.
Sorry, Professor.
Mm-hmm.
I didn't get the sign convention in this line. Why do we have V1 equals R omega minus V2?
Well, because the velocity in this point right here corresponds to the velocity of the belt. And the velocity of the belt is V1. And that's why we state that the absolute velocity, V1, is equal to the two components.
Okay, so it doesn't mean that R omega plus V1 equals V2.
It doesn't mean that?
Yeah, I mean, R omega plus V1 equals V2.
No, that's wrong, because R omega and V2 are components, and V1 is the absolute velocity.
Yes, okay, thank you.
Okay. With this relation, we can go back to the first kinematic condition and substitute alpha. Then we have I'll state it here. A2 is equal to 1/2 A1. And that's our second kinematic condition.
Sorry, Professor. So we know V1 is to the right because on the diagram it's drawn like this, or
V1 is the direction of V1 is given, the direction of the velocity one of the belt here.
Excuse me, Professor.
Mhm.
But how do we know the direction of V2? It's not given in the diagram.
No, but we have to derive that. So if the cylinder, the cable drum is located on the belt and the belt moves to the right, so then the rotational direction is this one right here, right? This.
Oh, okay, okay, okay. Thank you.
Yeah, and then the velocity has to point opposite in the point in the velocity pole.
I'm sorry. Excuse me, Prof.
Yeah.
I wanted to ask, can you please explain the acceleration A1, how it got to be 2r alpha? I understood the velocity part.
I built the time derivative of this. The time derivative of V1 is A1, and the time derivative of 2r omega is 2r alpha.
Okay, thank you.
That's what I said at the very beginning. If the kinematic condition is true, and for one kinematic variable, then it also is true for the time derivative and time integral of this variable. Okay, last example, 213. What do we have here? We have a planet wheel with a given radius. And again, it performs pure rolling around the stationary sun wheel, meaning that the wheel, the big wheel, capital R, does not move. Yeah, stationary, and it's also marked here that it's not moving. The rod, distance O to M, rotates with constant angular velocity omega-1. And the starting position is given with this relation, meaning that in the starting position, the angle phi 2 and phi 1 are both 0. So it started here. Okay. And again, we have to find the kinematic conditions and compute omega-2 and independence of omega-1 and phi 2 independence of phi 1. But of course, we know that this is simply the time integral of the first kinematic condition. So now it's one kinematic condition that we have to find the kinematic condition in terms of velocities. And then we have to build the time integral to state the same kinematic condition in terms of the angle. Okay, then again, let's do a sketch, a figure. Looks something like this. Then the directions are given, the directions of the angular velocity. And again, this wheel is not moving. Okay, this is stationary, but of course, this rod moves with omega-1. Then we have a velocity of the center of the planet wheel, like this. It's point M. So this is the velocity Vm. Absolute velocity of this point. And this point corresponds to the center of our planet wheel. Now again, we know that it performs pure rolling. The planet wheel performs pure rolling about the sun wheel. So this right here. Our stationary sun wheel, so it's not moving. In consequence, the velocity is 0. That's our velocity pole. Then we can say that we have our translational component, Vm, and our rotational component, small r for the planet wheel and omega 2 for the angular velocity of our planet wheel. Okay, so it's exactly the same as the wheel on a plane surface. Same figure, okay? This is omega 2. And this is omega 1. Now, due to the pure rolling, we know that the absolute velocity is 0. And in consequence, Vm is equal to r times omega 2. So what we want to find is the relation between omega 1 and omega 2, since the velocity Vm is not given in the problem description. But we can build the equation for the velocity of Vm, since this is nothing else than a rod performing a pure rotational motion. Point M rotates about the center of gravity, rotates about the hinged support. Then we know that Vm is velocity in case of rotational motion, radius times angular velocity, and the radius in this case is the capital R plus small r times omega 1. Then capital R is too small r in this case, so it's 3r omega 1. Now we substitute this into the relation above, and we obtain 3r omega 1 is equal to r omega 2. The radius cancels, and we obtain our relation omega 2 is 3 omega 1.
Sorry, Professor, can you repeat again what you did in Vm? Because I'm a bit confused.
Vm is the velocity of, in case of pure rotation. So M rotates, performs a circular motion about the center, O, the hinge support. And velocity in case of rotation is radius times angular velocity. And in our case, radius is the length of the rod, and the length of the rod is capital R plus small r.
Okay, thank you, Professor.
Yeah, okay. So this is all, so page number 1 in the formulary. Okay. And then if we found the relation for the angular velocities, we can simply integrate to find the relation for the angle. And that's it. Okay. So that's how it works. And we will solve several problems where we need this, and where we need to state the kinematic conditions. Because once we found them, we can apply our standard approach. It's a rigid body problem. Then we describe the motions by translation plus rotation, find the absolute velocities, and perform our computations. For now, I would like to do another example where we do not yet. Yes.
About the rod MP, is it moving or what is it?
It's moving with omega 2.
Oh, okay.
There, it's fixed right here to the planet wheel.
Okay, all right.
Yeah.
Thank you.
Professor,
Hmm?
why did you take the VM like R plus R omega 1? Why didn't you take omega 2 here?
Because this rod rotates with omega 1 and not with omega 2.
But we took the length of the rod like R plus R, and we should take omega 2 in that case. Shouldn't we not?
No, because this is this example is our robot arm. Often it's just our robot arm. That's our system. And this point rotates with omega 1, and this point rotates with omega 2. This is point M, and this is point P. So to describe the velocity of point P, it's a pure rotational motion about point O. Okay.
Okay. Yeah.
So Vm, and then it's simply, and this is the radius, R plus R.
Mm-hmm.
And then Vm is radius, R plus R, times omega 1, because the rod rotates with omega 1 and not with omega 2.
Okay, got it.
Okay.
I'm sorry, Professor, can we go to the first question so I can take a screenshot?
No, just talk to your classmates. Okay, let's do another example. Problem 2.8. We want to do two more examples of chapter 2 before we continue to chapter 3 and solve some more problems there. So I'll just have to copy it here. So, but if you want to look it up, 2.8, problem 2.8. No, let's go. Okay, so this is our system. And what we have is a 4-bar linkage, which consists of a rod, from the distance A to B. The length is given with 2L equal to 2 meter. And it's led by 2 bars that are rotationally mounted in A0 and B0. And we have to find the angular accelerations, alpha 2 and alpha 3. And the alpha 1 is given. And the whole system starts from rest position. So that's important for solving the problem. All angular velocities are equal to 0. So there are only accelerations, no angular velocities. And we have to find the acceleration of the center of gravity only in its components, X and Y component, according to the figure given. So we do not have to put the absolute values. So how does it work? The direction of alpha, the alphas are given. And now we have 3 different rigid bodies, and they are connected by joints. So what we can do is we can free the system and draw 3 different diagrams, one for every rigid body. So for A and B, and that's A as well. And we can include the center of gravity if we like to. Okay, now we have 3 different subsystems. Let's number them, and makes it easier to solve the equations later on. Now, just take a few minutes of time and draw all the accelerations needed. Remember, it's a rigid object. We want to use the approach translation plus rotation. So in red, we can draw the absolute acceleration to our specific points. And in purple, the translational component, in green, the rotational component. Okay, I'll just give you, let's say, 5 minutes to draw the accelerations.
Professor, are there 3 or 4 bars over here?
I can see 3 bars.
But the question says the depicted 4
It's
bar.
a 4-bar linkage because it refers to the joints. Yeah, it's yeah, that's right. The English word is a bit odd, but it's there are 3 bars, 4 joints.
Okay, so like, is AB actually 2 bars?
No, that's one. The AB is 1 bar, and B0 to B is a rod, and A0 to A is also a rod. As in statics, engineering mechanics 1, you might remember that the bars were always the thicker lines, or the 2 lines, and the single lines were bars or rods. Rods or ropes.
Okay.
Yep. Yeah, I just checked in the dictionary. 4-bar linkage. It's the translation for well, in German we would say 4-joint linkage. The German word refers to 4 joints, but in English the translation is 4-bar linkage.
Okay.
Yeah, it's a bit odd, but I don't know. Okay, let's have a look at the diagrams. Let's start with the first sub figure. Point B rotates about the hinged support, and it rotates. Well, it's being accelerated. The angular velocity is equal to 0. That means that there's only a tangential component of the acceleration. The normal component is equal to 0. So we could state here that this is our absolute acceleration of point B, AB. AB is equal to AB tangential. AB normal is equal to 0. Since omega, which one is this? Omega 3 is equal to 0. So this is our absolute velocity. Then for the second subsystem, it's the same situation. Omega 1 is 0, so there's only the tangential component of the acceleration. AA is equal to AA tangential, AA normal is 0, since omega 1 is equal to 0. Now we can transfer the absolute accelerations to the third subsystem. We are only able to transfer absolute accelerations, never only components. But since we know the absolute accelerations, we can state them right here. This is AA and this is AB. Now, if we want to describe the motion of point B, we can say, again, our standard approach, that point B moves translational as point A, and at the same time, B rotates about A. Yeah. This is the direction of alpha 2. Again, there's only the tangential component. ABA is equal to ABA tangential, since omega 2 is equal to 0. If you draw the normal components in the diagrams, that would be fine as well. You have to simply have to state somewhere at some point of your computations that these accelerations, that these components of the acceleration are equal to 0. Okay, and now if we start solving the system, we could start with the first subsystem simply by stating the equations that we have. I will just write in the space here as well, and we don't have to move up and down all the time. So for the first subsystem, point B, that ABN is equal to 0. We already stated that. I will not repeat it here. Then AB is equal to alpha 3 times L3, the radius, the length of the rod. Now we have to figure out the length of the rod, but that's quite simple. Let's have a look in this figure right here. We have this right triangle. This is L, and this is L. So this the length is square root of 2 times L. Alpha 3 is square root of 2 times capital L. Okay, that's all we have to do for the first subsystem. For the second subsystem, we have a acceleration of point A, which is alpha 1 times L. Alpha 1 is given. It's the only variable given in our problem description, and L is given as well, of course. Then this is 4 meters per square second. Okay. once we have that, we can move on to our third subsystem. And for the third subsystem, we use our standard approach, saying, okay, the acceleration of point B can be found by vector addition of the acceleration of point A plus rotation of B about A. I will state the vectors here. A, B, we have to find the angle first, but since we know that we have 45-degree angle right here, then this is a 45-degree angle as well. Then we have in horizontal and vertical direction, AB cosine of 45 degrees is 1 over square root of 2, and AB sine of 45 degrees is also 1 over square root of 2. And then this is equal to the translational component, which has only a vertical component AA, plus the rotational component, which points in horizontal direction. So it's A, B, A, and 0 in Y direction. So then this is quite simple to solve. We have two equations. Start with the second equation, since we know the acceleration, absolute acceleration of point A. So this variable is known. The other two are unknown. Then we have AB is equal to square root of 2 times A. And that is, see if I computed that.
It's 4.
Yeah, I didn't compute it actually. It's 4. No, it should be 4 times square root of 2. Well, we can 4 times square root of 2 meter per square second. I didn't compute the number because we were not asked to. But okay, then we have AB, and then we can use AB and substitute in the first equation. So that's from the second equation. And from the first equation, ABA is equal to our alpha times 2L. Then we have alpha 2 times 2L is equal to AB 1 over square root of 2. Then alpha 2 is equal to 1 over 2L, 1 over square root of 2, and AB is 4 square root of 2 meter per square second. Then square root of 2 cancels. We can cancel that. The length L was given by 1 meter. So we obtain alpha 2 by 2 per square second. Okay, then we have the first result. Once we know alpha 2, we can substitute this in our first subsystem, because there, from 1, we have AB is equal to alpha 3 square root of 2 times L. AB is 4 times square root of 2 meter per square second. Alpha 3 square root of 2, and L is 1 meter. then square root of 2 cancels. 1 meter cancels with meter. And then alpha 3 is equal to 4 per square second. Okay, that's the first part of the example in the problem. The second question is to find the accelerations of the center of gravity. And the center of gravity is right here. And of course, that's simply another point, and we can use our rigid body approach there as well. How do we get, well, our this is our standard rigid body approach. We pick 2 points on one rigid body and say this one point B moves translational as point A, and at the same time B rotates about A. We have a look at the formulary, second page. Then it's here, chapter 2, kinematics of rigid bodies. And it's this equation here for the accelerations. Okay.
Professor,
Yes.
is it also possible to determine the relation between the part 1 and part 3? Like I am thinking that B is rotating around B naught. Can I also approach the math with this relation? Like I don't want to make a relation between the part 2 and part 3, but I want to make it from part 1 and part 3. Like A B naught vector is equal to A B naught vector plus A B B naught vector. Is it also possible?
No, well, you have to use part 2 to compute the acceleration of A, because otherwise you do not have enough information. But of course, you could describe point A instead of point B. So you could write AA is equal to AB plus AAB. Yeah, that would work as well.
But I cannot make it like part 1 and part 3. I cannot make the relation between these two.
No, because that's not enough. You also need part 2, because you only know alpha 1, so the acceleration of part 2. And without this acceleration, knowing this acceleration, you're not able to compute the rest, because we do not know the alpha 3 for part 1. You cannot compute AB directly.
Like in the exam, if the alpha 3 was given, then I could have gone through that approach.
Yes, then you could have used that approach.
Oh, okay.
Okay, but you still would need A1 to find, because you're asked to find all angular accelerations, then you would still have to move on to part 2 as well. Okay. So now, wait, the center of gravity, acceleration of the center of gravity. We can simply choose the components or state the components A, C, Y, and A, C, X. And now we use the same approach. We say, okay, the center of gravity moves translational as point A, AA, and at the same time, the center of gravity rotates about point A, like this. And if you have a look at the diagram, it will be really simple to find these variables. So what we say now is AC is equal to AA plus ACA. And then for the vector components, we have ACX, ACY, which is equal to the acceleration of point A, which only points in vertical direction, and the rotational part, ACA, only points in horizontal direction. And ACA, again, is alpha, which alpha? alpha 2. And now the radius is L. So alpha 2 times L, and there's no vertical component. And then since we already know alpha 2, we can compute alpha 2 was 2 per square second times 1 meter. So it's 2 meter per square second, and A was 4, given the 4 meter per square second. So
C is the middle point of AB.
C is, yeah, the center of the rod AB. Okay, other questions? Well, if not, let's have a look at a very similar example, and then you try to solve this on your own. We will start solving it and continue in our next class. So we'll have a look at the next one, 2.9. Again, I have to copy it first. Okay. So it looks very similar, rotated by 90 degrees. And instead of 2 hinge supports, we have 1 hinge support and 1 roller support. And now our system has angular velocities. So we have this bar rotationally mounted. The bar AM, length is given with 50 millimeter. The angle beta is given for this rod AM, and it rotates with constant angular velocity, 10 radians per second. The second bar, distance BC, is given with 25 millimeters. And this is mounted in a floating bearing, roller bearing, and rotates with constant angular velocity omega 2. Both bars are connected by a rod, and the rod AB with a length of 200 millimeters. So in the first part, we have to find the velocities of A, B, and C, and the angular velocity. And in the second part, we have to find the according accelerations. So for now, just take like 5 to 6 minutes of time to draw the diagrams for part A, for the accelerations. So only include the accelerations in your diagrams. We have 3 rigid bodies. In consequence, there are 3 subsystems, 3 diagrams that we have to draw. Okay, so try to do that on your own. Okay, that's how it should look like. We have the simplest rod is the rod AM, the pure rotation of A about M. So the absolute velocity is the velocity due to the rotation BA. And we can transfer this absolute velocity to the horizontal beam. Then for the second subsystem, the rod CB, we have the translational motion of point C of the roller support, which is the absolute velocity of point C. Then for point B, the upper part of the rod, we do not know the direction of the velocities. So we assume simply an X and Y component. And then again, we can use the rigid body approach by stating that VB moves translational as point C, and at the same time, B rotates about C. So red is purple plus green. And then for the horizontal beam, we do the same. We can transfer the absolute velocities of point B, the red vectors, and we can say that B moves translational as A, and at the same time, B rotates about A. Okay. So that's how it works. And once we have the figure, we can state our vector equations and then just go step by step solving the values, the velocities in this case, and the angular velocity. Any questions so far?
Excuse me, I have one question concerning the velocity of VB. Why is it in two-dimensional, that's y and x? Shouldn't it be just be VB towards the x direction only?
Well, in general, we do not know the direction of VB. And so in general, we assume a horizontal and a vertical x and a y direction. But of course, from the second subsystem, the rod BC, we can already see that the vertical component, VBY, will be 0. But to make it complete, I included it here. But of course, you're right, it will be 0.
Okay, because I actually solved this question before and I was able to get the A part of it. But because of the B part where I was trying to solve, I was not able to get the alpha 3 because the equation was not complete. Now I understand my mistake. Thank you very much.
Okay, yeah, you're welcome.
Professor, I have a question. In the horizontal bar, why have you denoted VA again on the right joint, on the joint B?
Well, that's a purple, so that's our translational component of the absolute velocity of B. So as always, as we did in the previous problems, red is equal to purple plus green. So we assume B moves translational as point A, purple vector, and at the same time, B rotates about A.
Okay. Do we also need to represent VC at the point B on the horizontal?
Yes, yes. Of course, again, for this part, B is the absolute velocity of BC, purple plus green, BPC. So always purple and green are the components and red is the absolute velocity. And if we use the vector equations for these points, point B in this case, we have to draw the vectors there that we use to solve the velocities. Okay, other questions? Okay, if not, then I wish you a good weekend. Monday is a holiday, as I said at the beginning of the course, so there will be no class on Monday, and we will continue at this point Friday next week. Okay, then have a good day and see you next week. Bye.